Hi everyone, welcome back. Alright, today we're going to talk about how Haskell actually evaluates expressions. So here's a review of what we've done so far. Haskell is this functional programming language. It's strongly typed, it has type inference, so you don't need to specify the types. And the types we looked at are booleans, and these particular classes and types. There's the class of equality and odd, and we also looked at the tuples, lists, and function types. All right. We'll also have to know about classes and type variables. And then we've looked at a few abstractions that we're going to look at. So we looked at list comprehensions, the list of f of x such that x is an element of the list and some condition of x is true. So list comprehensive are very flexible ways to actually build lists. And we looked at two other abstractions for lists, so we don't have to write recursive definitions because we've seen a pattern that arises of different programming, so we try to abstract that pattern and write down a new abstraction that makes so we never have to write that pattern again. So the first abstraction is this right associative binary operator to reduce this, and this is called fold R. So given the arguments, it does this function here, it does this right associative, and it keeps applying that. The other one is fold L, which does it on the left side. So it does this, given this value here, it applies it to A1, then the result of that applies to A2, etc. All right, so let's have a look now at how we're going to evaluate expressions. So the first thing is to recall the definition. Recall that foo of x is x. So if you have foo of x as some expression, is an abbreviation for this. So foo is equal to this lambda x goes to expression. Alright, and writing foo is the same as writing this lambda x goes to an expression. So we can think about those as just a definition. So one is just replaceable by the other. And with two arguments, well, it's an abbreviation for this. Given foo is this function, which given an x returns another function, which given a y evaluates to give the expression. And x and y typically are parts of the expression. Okay. There's really only one operator that we have to worry about, and that's this reduction operator. So if we have lambda x f of x, so f is an expression which has x as which x appears in it, and we apply it to the argument a, then that reduces to f with x replaced by a, so f of a. Okay, we're just going to substitute the argument here for the formal parameter, and that's why f of x becomes f of a. And that's really the only operator, the only thing that happens inside Haskell is this reduction. And that's how evaluation works. Okay, it's simple. So is this, so suppose we have m of xy is equal to x times y, a simple function. And we have m of 10 minus 15 and m of 10, 15. Right, so there are two m's here. There are two different ways of doing the evaluation. One is called by value, and this is the one we're going to see that's familiar with many programming languages, is you're going to evaluate the arguments before reduction. So first of all, going to evaluate 10 minus 5, and you get 5. And then we're going to do m 10 of 5, and we get 10 times 5 is 50. So we end up with m 5, 50. And then we evaluate that, and we get 250. The other one is called by name, which says we're going to replace m of xy by, we're going to replace this, before we evaluate the arguments, we're going to replace this for x, we're going to replace this for y. So in this case, we'd end up with 10 minus 5 times m of 10, 5, and we get, and this becomes eventually, this one here, becomes 50, this becomes 5, and we end up with 250 again. All right, so there are the two ways of evaluating things. So here's the review again. Call by value, evaluate the arguments before reduction, and call by name as we do reduction of the function first. All right, now think about what the following does. If you say inf equals 1 plus inf, then what happens here? Try it in Haskell. Type it into Haskell and see what happens, then type inf and see what happens. But remember, this inf is the same as this inf. So whenever you see this inf, it replaces it by 1 plus inf, and then it has this inf, and that replaces it by 1 plus inf. Okay, so just see what happens when you try it in Haskell. It's also interesting to check how much runtime is being used, so try that. All right, And now we're going to think about the following one. So we have inf is 1 plus inf, like before. And we have fst as this built-in first function of x, y is x. And now we'd like to do the first of 3 plus 2 and inf. Well, if we evaluated the arguments, so if we just apply this and substitute it, we just end up with 3 plus 2. If, however, we evaluated this pair, we'd end up, this becomes infinite. So we get into trouble. So if we just substitute the values in here, we'd end up just as 3 plus 2, right? Which we can evaluate as 5. If we didn't evaluate the arguments, we might not get into it. We might get into trouble. Okay, here's another example. Let's do square of x times x. Well, you can evaluate 55 plus 45 and you get 100. And then you can do 100 times 100, gives you 10,000. The other way of doing it, that's called by value. And called by name, you'd replace this with 55 plus 45 times 55 plus 45. And if you think about what's going on there, you have to do this addition twice. Right, so call by name seems to be wasteful of resources. Right, so you call by name. If we evaluate it first, we only have to do the addition once, do one multiplication. If we substitute first, then we have to do 2 additions and 1 multiplication. And if you think a little bit about that, this can get arbitrarily complicated. You can redo expressions over and over again. Okay? It turns out that if they halt, they both give the same answer. So if call by value and call by name halt, they both give the same answer. However, sometimes call by value does not halt. All right? So what Haskell does is what's called lazy evaluation. It tries to get the best of both worlds. So it evaluates the arguments only once, but it only evaluates them if it's needed. And if you think about it, this seems sensible. You only want to evaluate it once, but if it's not needed, you shouldn't evaluate it. And then you can do the evaluation ordering. It evaluates from the outside in. So you evaluate from the outside of the expression in. Otherwise, if it knows the arguments need to evaluate, it's going to go from left to right. So if it needs to, so if it evaluates left, it might get a lambda form, then it's going to go from left to right. Okay. Now, it's possible to evaluate all the arguments that needed to be evaluated in parallel. I'm not sure that GHC does it. You're certainly allowed to do it. I think that one of the reasons that Facebook uses Haskell for all of its internal work is because it actually can run everything in parallel and still get the right result. Right? Doesn't matter. You might as well run in parallel. It just saves time. You're still going to compute the same result. So it's a nice way to do a parallelism, and you can actually do, you're still going to get the same results. So parallel evaluation also gives the same results. But you also only want to do it if you need to do it. And one could imagine a language that remembers everything, results of all previous function calls, and that would also be a legal Haskell. GHC does not do that. In fact, as far as I know, that no Haskell compiler does that. So basically, space is usually an expression. It just caches this locally. It just remembers very locally what's going on. It just remembers locally that's already computed this argument, so it doesn't have to do it again. It doesn't do it globally, although it could, and still be correct. But what lazy evaluation now enables a form of programming that's not possible with call by value. Right? So if the definition of if then else, here's the definition we saw of if then else before. It's my if, and if the result is true, and given the 2 arguments, the then expression and the else expression returns the then expression. And my if is false, takes the then expression and the else expression and now just evaluates the else expression. Right, we can define factorial of n, saying my if n is equal to 0, we're going to return 1. Otherwise, we're going to do this recursive definition. Now, if we did call by value, right, then this always goes into an infinite loop because this gets evaluated whether or not n is equal to 0. But lazy evaluation lets us write this. So it lets us do things now that we couldn't do before. So it lets us have interesting new programming paradigms. So lazy evaluation not only in some sense is more efficient because it doesn't do things unless it needs to, and it can recognize that at compile time, but also it lets us do different interesting programming. So here's an interesting example. So there's something called the sieve of Aristophanes. And the idea is you start with a list of all numbers greater than or equal to 2. So you're going to start off with all of the list of all numbers. And when a prime is found, you're going to cross off all the multiples of that prime from the rest of the list. So you're going to find 2, then you're going to cross off all multiples of 2 from this list of all the integers, list of all the numbers. And then you're going to find 3, and then you're going to cross off all multiples of 3. And the next thing you're going to find is 5, so you're going to cross off all multiples of 5. Okay, that's the sieve of Aristophanes. Okay, and we're going to implement that as a function called sieve, which is going to take a list, and this P is a number, and this is going to be the list of all primes of P, given all the multiples of P have been less than P have been removed. So we're going to return the list of all the primes, and we know in here, in the argument, that all of the primes less than P have already been removed. So the first thing to notice is that P is a prime, because all the lowest multiples of it have been removed. So now we've just got a recursive call of sieve. Okay, so try and do that, implement it. It's in Lazy if you want to look at it, and then we'll play with it in class. Okay, that's all. Thanks all, everyone.